Well, hi, this is Peter Warren, and I'm going to talk about ventilation, and in particular mechanical ventilation, heat recovery, and good practice, or basically how not to mess it up. We're just a bit of background. We're a team of actually 6 now, small business in Plymouth. We work mostly on passive house. We do a lot of dwellings, schools, OAPs now. We also, alongside design work, we also do training and we certify. And we're very interested in actually finding out a bit of R&D and what actually works. So what are we going to talk about today? Well, why we like mechanical balanced ventilation, and particularly with heat recovery. It is a bit weird. We know they always have this problem where people think we're going to make this airtight and then we're going to cut holes in it and put fans in. It always seems a bit weird. We're going to talk a bit about that, and a bit about comfort, and a bit about filters and the role of filters. And then really what we're going to start looking at is the good practice bit, main part of the talk. We're going to look at airtightness, fundamental prerequisite. Look at design issues, some hybrids of MVHR and commissioning, and then a little simple exercise just to see how much you've picked up from what we've said, and then we'll have a summary. So here we go. Let's start off with normal ventilation or natural ventilation, and just the way this works. And I've got the Part F figure up here, pinched from the online building regs document. And what's really going on is that we have this is natural ventilation is really driven by wind pressures. So you've got pressure one side of the house, suction the other, and stack pressures, which is basically to do with the house being warmer than outside. So cold air comes in the bottom and exits through the cracks around the loft hatch. And that's very much what we do. And on top of that, we put extract fans in to run intermittently, showing them here. It's one in the bathroom, one in the kitchen. And these actually just maintain ventilation when the wind is very low speed. So to make this work, however, you see by the dotted line around the house, we actually have to have a leaky structure. Because to get the background ventilation going. And I think it's probably realistically to say that this is the biggest single issue with low energy and natural ventilation, is that to get enough ventilation during most of the time, you have to over-ventilate a lot, and so essentially you're getting far more ventilation than you need. If we look at balanced ventilation, here's another picture from the mechanical ventilation with heat recovery, and there's the unit in the attic, a dreadful place to put it. What we'll see is that this system here basically supplies, it's a balanced system, it's supplied and extract, both powered by fans. And our MVHR, mechanical vent heat recovery, and the wind pressures and the stack pressures are still there, but we aim to have a perfectly airtight envelope, so that whatever the wind and stack pressures are, you get a constant ventilation rate at the kind of low level. And to add to that, we can put the heat recovery on. This is the only system you can really put heat recovery on. Okay, so and what you can do, you can actually get a independent airflow of external conditions. So you've got a nice constant airflow. There is a bit of a warning about this, as hopefully you'll know at the end, that this particular picture is really illustrates lots of things you shouldn't do, and by the end of this talk I hope you'll recognise it, so I'm just going to say that now. Okay. So very quickly, heat loss, how it all, ventilation, insulation and heat recovery, how they all add up. This is a very crude picture, but if you think of insulation, you can reduce the heat loss through opaque elements such as walls, roofs, floors, to practically zero, really, by adding enough insulation. There's no theoretical limit. Ventilation now is slightly different because we need a level of ventilation. You can't be zero. And so you could think of it very crudely of having an existing building which has got fabric heat loss, that's our insulation, and ventilation heat loss like this. And if you insulate it into a really good super insulated passive house job, you'll affect the fabric, but you won't affect the ventilation. So we need to actually go down to get to low energy buildings. We really need to add in heat recovery as well, and that's the kind of overall logic about what we're doing. Then just a little brief mention about comfort. Comfort's very important. It's essentially what we're trying to provide. We're not trying to provide a temperature, we're trying to provide comfortable conditions. And my favourite definition of comfort is if it's really comfortable, you don't even notice it. And so actually, that's another way of saying what we actually notice is discomfort. So here we go. And the important things about comfort and ventilation is drafts. If you get air moving more than 0.1 metre per second, which is not very fast, or if you get air entering more than about 4 centigrade colder than the room temperature, you'll get a downdraft, and you'll get the 0.1 metre per second. As soon as you get that and it touches you anywhere on back of the neck, the waist or the ankles, if those are bare, you'll need to add 1 to 2 degrees C higher room temperature to get the same level of comfort. So we need to get rid of drafts, okay, which is probably, I would suggest, only realistic if you're going to go for the airtight route. Brief thing about filters. I mean, I love this pair of pictures which came up here. I saw on one of the slides, one of the leaflets for this talk. And I think there's something slightly wrong though. I think they've got the filter on the wrong person, because, well, certainly outdoors is not always nice and fresh, let's put it like that, and it's probably got pollen in it anyway. But certainly, I mean, when you look at these are the filters which came out after a few months in London. You can see that outside air is not necessarily what you want to be breathing without some form of filtration. Okay, a few definitions. Ventilation is the amount of air which goes through a building. It can go through the windows, through the cracks, or through extract fans. And it's controlled by the occupant. That's the whole point about it. However, the infiltration is not controlled by the occupant, and that's basically the cracks. Sorry, I said it was the cracks on this one. It's not so. The infiltration is what you can't control. It's the leakiness of the building. It's at the mercy of weather conditions, and of course, can be measured by putting a fan in. And here we have a picture of a fan measuring the air leakage, and the standard pressure, 50 pascals, quite a lot more than average stack and wind pressures, which are about 4 pascals. But what you get is a measurement. An air leakage, an air pressure test is a measurement of the infiltration, the leakiness of a building. Okay, so just so we understand that. And here's a picture of my friend John Willoughby doing an air pressure test. There's the fan, depressurising and pressurising. And it's worth knowing that, according to how leaky your building is quite important in terms of determining what sort of ventilation system you should be putting in. Max Sherman, who's one of the very early workers in low energy buildings in America, from Lawrence Berkeley Laboratory, very famous source of a lot of good data and understanding. 1998, he produced this paper, and basically what he was trying to do was to say, according to how leaky the building is, what sort of ventilation system is appropriate. And just you don't need to read all this, but just let me highlight something that he's saying his category A, which I would say is it's a one air change at 50 pascals, which is the passive house Enerfit, the retrofit standard, is he's recommending a balanced type. In fact, he's actually saying only balance works for that. And if you go to a good retrofit standard, maybe not up to Enerfit, you may get between 2 and 3. And what he's saying is you can use a balanced system, and balance means you're supplying and extracting the air. Okay, so you're not depending on the leakiness of the building. And even up to 3 you can use either. I mean, I would suggest that typical stock is anywhere 5 to 27. I think 5 is, when you've got a building that's up to 5, he's suggesting either. I think actually that leakier building, it's not worth putting a mechanical ventilation heat recovery unit in. And we need to be really clear about this, that if you're going to do a project and you're thinking about doing a very low energy project and you want to look at different types of ventilation, if you're going to put mechanical ventilation in, you must be aware that you need to get, to make it work, you need to get the air tightness of the building right down to make it effective. Yeah, certainly in the 3 and below category, I would suggest. Okay, quick look at MVHR. There's the unit itself. What's it got in it? It's got a pair of fans. It's got a heat exchanger in the middle. It's got filters. I mean, that's basically it. And the air comes in from outside. It's cold. That's blue. Gets heated up in the heat exchanger and taken out the supply. And conversely, the air from extract from the house comes in through the other filter, another fan, and gets cooled down by the air coming in and is given out as exhaust. So very simply, the fans, we want them to be as efficient as possible. DC fans almost certainly nowadays. We want the heat exchanger to be as efficient as possible. Counterflow generally, and obviously none of the air needs to mix between the two streams. And the filters, very important part, because if you saw those pictures earlier, depending on where you live, the frequency of changing is important. And it's interesting that filters were initially seen as a way of protecting the heat exchanger, but if you see some of those filters and you think, well, actually, I really don't want to breathe that stuff at all. So here we go. Now we can actually go to how you can make your MVHR work well. Alternatively, you could say how to cock it up, how to make a mess of it. You've gone to a lot of effort to make an airtight shell. You put insulation in it here. And so when it's warm inside, it's cold outside. The air in these two pipes joining the MVHR unit to outside is actually, well, one of them's cold air, so it's coming straight in, is actually the same as ambient. And if this is anything like an efficient heat recovery unit, then the air going out is also close to ambient as well. So these two pipes are basically like outside. And so the insulation on them is absolutely critical. If you've spent a lot of time on passive house projects, you may have 200, 300 millimetre of insulation, and then you have these ducts going in, and if they're very long and they've only got, I don't know, either nothing or 25 mil of insulation, I mean, that's a huge heat bridge that you're putting into the building. So you need to be very careful about these, and what we suggest you need to do is two things. You need to insulate them, obviously, but the primary thing is you need to make them short. And what that means is that you have to put the MVHR on the outside edge of the fabric, right next to where it's going through the wall. That's the best thing you can actually do. And that, of course, means you've got to design it in from the beginning of your project. Okay. Something else, this is a fairly old photograph, but you do get a lot of manufacturers giving this sort of impression that you can just stick the MVHR in the loft. Very bad idea for a lot of reasons. Well, one is obviously they haven't insulated any of the pipes, which is appalling. But also in this is that you can see that their distribution is going through the loft insulation. Well, if you have a system like this with lots of pipes going through the external insulated fabric, you're really threatening your air tightness. So, almost like this system is going to have a problem because you're actually making more holes through the house fabric itself. But more fundamental is who's going to get up there and change the filters regularly? Who's going to get up there and check them? I don't think putting it in a loft is a good idea because of that. So here we go, yeah. Thirdly, it's really important to think about the ductwork and the layout and how it's all going to go together early on. This picture here is showing some small bore ducts, and you'll notice that some of them are doubled up to go to some terminals. These terminals up here and down here have got the blue and the red have got two ducts, and basically what you need to make sure is that you're not increasing your fan power by squeezing in very, very small ducts. Okay, you need to make sure generous sized duct. And usually for domestic, that's 150 mil for your main run. This one here says 125. 150 I prefer, and obviously that's a fairly chunky thing to fit in, including its bends. So you have to actually make sure you can do that. And the other thing, of course, you have to design in is that you have to actually eliminate noise from the fans. A good MVHR system should be completely quiet. If it's not, that's not really a good idea, I don't think. You also need to be careful because you can actually get crosstalk, which is, you need to lay out to allow for noise going up one duct and along and back and not coming out to another room. So you can't actually hear what's going on in the other room as well. So you need to actually pay some attention to the layout, the ductwork layout and design very early on, because silencers tend to be quite chunky, ductwork is chunky. You need to get it designed, basically. So once you've you've got the general ideas about what you're going to do with the ductwork, you need to minimise it. But two little tricks that we use a lot in Passive House to actually shorten the ductwork. The first is using coanda terminals, and this is basically there's an effect called coanda where if you blow air into the room under a ceiling, it sticks to the ceiling. It doesn't diffuse as long as it's within about 8 inches. 200 mil, you can get 6 metres across the room easily. And what that means is you haven't got to take the ductwork on the other side of the room, and your supply and extract are on the same size. That can make a substantial reduction. And here are some coanda terminals. The little slot ones we use for domestic. There's a ceiling one there that can blow out. You can block off half of it and blow in one direction or another. And a picture of the school classroom behind showing a big slot diffuser using the coanda effect to blow air across the ceiling, across the other side. The other trick is a thing called cascade ventilation. Relatively new in the Passive House world, but increasing attention coming to it. What it's about is very simple. You actually, rather than supplying every rather than extracting every wet space and supplying every dry space, you try and cascade them down. So here's an example. Here's a flat. We've got one inlet into the sleeping area. It comes through the door, through the gaps from the door, into the living area, through the corridor. There's one extract in the kitchen and there's one extract in the bathroom. So you've only got 3 terminals, very little ductwork for the whole flat. So these are the kind of tricks that we like to use. So, the other thing you need to think about is just a bit of care about where you're going to take the air from. Unlike good old natural ventilation, it sort of comes from all directions, and if there's a particular smell in one direction, it all gets sort of evened out. In VHR, you tend to take the air one place. This is the series of passive houses in Austria that we visited, and somebody asked the very awkward question saying, why is the air intake in the cupboard, in the dustbin cupboard? Which there was some embarrassed discussion amongst the people showing us around, and they said, oh, well, it's actually a mistake, we're going to move that. And I should hope so too, because that's not a good idea. It's also not a good idea because of cars. You can just imagine someone backing in here, and they start their car up in the morning and exhaust straight into there. And I think in general what we tend to say is we don't take low-level input at all. You also need to be a little bit wary about chimneys. I know my friend Andy Simmons has got a retrofit passive house in Hereford. He's got wonderful high-level input, and one of his neighbours has got an open coal fire that they light up every now and then. If the wind's in the wrong direction, you get it. So there are some issues about thinking about where you're going to put the terminal. Okay, last point, controls. Really, really important, this. Making the controls appropriate to the user. This is the sort of thing I like to see. It's got 3 buttons, 3 speeds, and it's got a boost, which has got a timer on it, so it'll just run back, okay. And there's a little filter indicator as well, it tells you the filter that is changing. That's what we want. Unfortunately, what we tend to get is a lot of these, which are fantastic for people like me who like delving into the operating system and changing it, but frankly are a bit of a joke really for normal human beings. You also need, as well as having the good controls, you need to tell people how to use them. Page in the manual, I mean, this is typically the amount of text you need, not a lot, very simple. But also, you need to think, where is this control going to go? Because there's no point putting it up in the upstairs, I don't know, hot water cupboard or something like that. It's just because people aren't going to use it. You need to put it somewhere in the main living area. So location is very important. Okay. So a very quick look at, I see I've taken 20 minutes already, a very quick look at the other heat recovery options. Just mention this HRRV, which heat recovery room ventilation, which is basically a MVHR in a box, if you like. It's in one place. There's no ductwork. Fantastic. That is really what it is. A little one that you can put in with a core drill, nice 6-inch core drill. We've used loads of these, brilliant little things. However, there are issues with these. We've done a couple of houses, and although they've got no ducts, you've got to recognise that if you've got a lot of these in a house, because usually it's one per room, if you get a good wind exposure, then the wind will just overpower the fan and just blow in through one and out through the other, which really isn't what you want at all. So there are a bit of issue. And the other issue with them is apart from the very low speed, the 2-watt setting, if you actually want to get up to normal ventilation rates, you get a bit noisy, which is a bit of an issue. However, having said that, we have for many years dried our clothes in a little utility room with these in winter. And at 2 watts, okay, it takes 36 hours for a heavy load of washing. It just is brilliant, and much better than dehumidifiers and 100 watts, all that sort of thing. So useful in some cases. The other thing I'm going to look at very briefly is the I don't know how to pronounce this, the EAHP, exhaust air heat pump. We in passive house terminology we call them compact units, and what it's about is saying, well, the heat exchanger isn't 100%, it's sort of 85 or 90%. So some heat is still available in the exhaust air, a little bit. So what they do is put a heat pump on the back of it to recover that, and you can put that either into space heating or put it usually into water heating. However, there are some issues, and here's a picture of one, and the green bit is the MVHR and the red bit is the heat pump with a hot water cylinder in the bottom half. And the issues really relate to there isn't a lot of heat left in the air. So there's an awful tendency for manufacturers to up the airflow rate through the building so you can get more heat. But if you think about that, that's mad, because you're eating your own tail. So you've increased the heat load so you can recover more heat load from it. Silly. So you really need to be very, very well insulated before you can think about using these things, I would suggest. And there's also the issue of a lot of them have on-peak backup, which if it's not set up right, it can cost you a small fortune in electricity. Having said that, off the gas grid does provide a simple one-box solution, but at a price. Okay, so I've given you some ideas, and I'd like you to look at this slide for, I'll give you a minute. And this is a plan of, it's one floor of a 3-story building. And what you've got to look for is saying, where are you going to put the MVHR unit? Where in here? There's 2 flats. There's one here on the left, apartments 1 to 3. There's 3 floors of this. There we are. And apartments 4 to 6, slightly smaller. That's a 1 bed. So where are you going to put the MVHR? So I'll give you just a few seconds to look at that. I hope you can see it okay. Where are you going to put the mechanical ventilation heat recovery? And remember, there's the box itself, there's also the ducts. And remember what I said about you need it to be on the edge of the thermal envelope somewhere. Okay. Well, I can't hear you, but I'm going to guess that a lot of people are going to say, oh, a little services store here, we could put it in there and straight through. That's perfectly true, but the real answer to this question is actually to, rather than put it in there, which is actually outside the heated envelopes in the communal lobby, the real trick is to look at this and just say, well, actually, this layout's been designed by the architect, but actually doesn't suit an MVHR, and what we need to do is to change it so it does. And so what we're going to do is precisely that. And here is the slightly drawn up slightly, but the jiggled layout. And you'll see that the cupboards outside have gone. The service, the stairs have been moved up. This communal space has been shrunk. There's now a cupboard by the door for the MVHR unit to go straight to the outside. So it's very easy for access for changing filters and whatever. Once you can get through all the coats, I expect people will put that. And yeah, we've got a hot water cylinder location as well. Okay. So the whole point is, you have to really think this through. The MVHR will affect the way the rooms actually go together. Okay, another little question for you, and I took this from the initial flyer for this course. It's a bit fuzzy, blown up. Again, the question is, what's wrong with this? I came up with 5 things, I think. 4 things? 5 things? Give you a few seconds. Okay. Well, we'll start with the easy bits. The first thing is there's a lot airtight, and there's a loft hatch. That's a pretty tricky thing to do, and I mean, I have to say that the insulation levels are pretty. Looking at the thickness of this, is pretty minimal. Given that they're going to spend money on MVHR, they haven't bothered to do the basic insulation measures properly yet, so it doesn't sound right to me. And are they expecting people to come up through here, through this loft hatch and change the filter or inspect the filter? Is that realistic? Here's a bit of a subtle one. External terminations are on different sides of the building, so when the wind's blowing quite strongly in one direction or the other, you'll get quite a big pressure difference across it, which will alter the balance of the unit, the supply and demand. I personally prefer them to be on the same side. You've got to have them a certain distance apart to make sure you don't get any short-circuiting, but I'm not so keen on that arrangement. But the big one is they haven't insulated the ducts. And if you assume that one of these is a modern unit, 85% heat recovery, say, I make that about 1.5 meters each side, that's 3 meters. We put it in our passive hours calculator, and it says, no, it's not 85 anymore, it's 70. So, a real issue these. Okay. So, quick summary on design. We've got an airtight shell. You must have an airtight shell if you're going to go for the mechanical ventilation, balanced mechanical ventilation. Aim for 0, except less than 3. You need a space for the unit and the ducts on an external wall to minimise the insulated length. You need large ducts, but you need to minimise them. Acoustics are important, need to be designed in terms of attenuators from the unit, from the ducts and from crosstalk. Frost protection is an issue. All I'm going to say is you need to consider it, make sure the unit's got it built in. Otherwise, remember that the units all have a condense connection, and if you get very, very cold air coming in, which happens in some part of this country, the unit will freeze up, which you don't want. Control suitable for user we talked about, and this is just a relatively new thing. In terms of commissioning, our advice is very strong now. We don't believe that MVHRs get commissioned properly in this country, and we are now suggesting quite strongly that you actually go and get an MVHR that is self-balancing within a certain range, which means that basically it will alter the airflow through one side, say the extract, to match that through the supply. And lastly, I mean, as you can see, it's quite a complicated issue, the whole business. If you're new to this, we're really saying, look, we go to a one-stop supplier who can do the design, who can supply and commission it, because at the moment there's simply not enough people out there who know what they're doing, I'm afraid. So there we go, quick thank you, and just last message from us. We're happy to work with anybody who wants to do low energy passive house, and we're very happy to look over schemes at concept stage early as possible. And there's an email and a phone number. So thank you very much. Thank you very much for listening, and I really hope this helped you in your project. Cheers.